Okay, so now we're going to see how we can apply this theory that we saw previously, how we can use it in practice in TensorFlow with some practical problems. I'm also going to talk about the exercises for the tutorial now. But first I'm going to talk about graph mode, which is something that we can use to improve performance in TensorFlow, basically giving TensorFlow the whole computation graph so it can optimize how it's going to execute it. We're not going to use that for actually training our models, because there are lots of details then in graph mode that make things a bit more complicated, but we're going to use it to write the graph, the diagram for our model and for all the computations into Tensorboard, the logs. So I'm going to talk a bit about Tensorboard, and then we'll see some problems with the numerical stability and some details about the exercises. So Tensorboard is a utility, a suite of visualization tools that you can use in parallel with the training of your network. And this is a program that you set running, and it's going to read logs that you can write during training, so that you can then use the browser to access those logs and see, for example, the plot of the training error of your network as the network is training, or see other information that you can put there, or things like the graph of the computations to help debug your network, for example. So to do this, Tensorboard expects you to have logs in a folder. Let's call it, for example, the logs folder, and each run to have a different subfolder where it stores all the logs for that run. If you store logs for more than one run in the same folder, then all the plots will get mixed together and it will be hard to see them. So in order to automate this, you can use this trick, which is import the datetime module and create a string with the timestamp. So this is year, month, day, hour, minute, second, and you will have a string with the timestamp of the time you set your script running. And then you create a subdirectory on the logs dir with the timestamp string. This means that every time you run your script, you create a new folder and you put all the logs inside that folder. This way, all the runs will be separated and it's easy to use to see Tensorboard. Now let's use the logistic regression model that we used last week as an example. So I create here one neuron, which has these weights and the bias. This is the prediction, which is multiplying the weights by the matrix with the input and then applying a sigma activation. Note that I'm assuming that the input is a tensor here, so I'm not converting things into tensors. This must come as a tensor for this to work. I am creating here the logistic loss, which takes the predicted value, so the output of the neuron, and a tensor with the labels, and I compute the mean. This is the logistic loss function, so the product of the classes by the logarithm of the predictions. So this is for those that are in class 1. Those that are in class 0, this is 0 here. And then we have the 1 minus the class multiplied by the logarithm of 1 minus the prediction. So now I can compute the gradient, I compute the predicted value, and then the logistic loss. So remember from last week we saw this. We create a gradient tape object here, and in the context of that object, we run the whole computation. So this means that the gradient tape can trace all the computations between all these tensors. And so then we can ask for the gradient of the loss function, of the loss value there, with respect to the variables that we need so that we can train. Okay, so now we're going to use the autograph implementation in Tensorboard, in TensorFlow, which is the part of TensorFlow that can automatically trace all the computations and create the graph for all the computations. And we're going to use that. This is implemented in this TensorFlow function, and we can use this as a wrapper. So basically, this decorator here calls our function, create graph, inside the TensorFlow function. And that's the one that's going to trace through all the computations and build the graph. So one thing we can do here is we call this grad function here, which does the whole computation. So if we do this, we're going to trace through the complete computation, and we have both the prediction and then the logistic loss. Now, if we want to see that, we can do it in Tensorboard by creating this summary object here. So we call this trace on function on the summary module. It means that with graph equals true means that the summary module is going to write to the log the graph of the computation, and we're going to create the graph there in TensorFlow. So that create graph function, since it's inside TF function, will be used to trace all the computations that we need. And now we can use this writer that we created here. So writer is a file writer object that you can find in the summary module that basically allows us to write things to the log. So now we're going to export this trace, this computation graph. We can give it a name, and you generally associate everything you export to the logs to one step in your computation. This is useful mostly when you're storing, for example, the loss function during training or the validation error or something like that. But it's the general syntax for all of these things that you export to the log. So basically, we create this object so that we can write to the log. We, in this function here that we call afterwards, the write graph, we will turn on tracing and create the computation graph and then export that into the log. To make the log dir different on each run, we use this trick here. So we create this folder for the logs for this particular run using the timestamp of the time we are running the script. This create file writer creates the object that we can use to write things to the log, and we can do this writer as default to set this object here as the default writer. So when we do things like trace export, the summary modules knows which writer to use to export things to the log. So basically, these are operations that we can use to export information to the logs. And in this case, we are using this to show the graph of all the computations. Now, this part here, where we use the TF function to create the graph of the whole computation. So in this case, just one detail here, so that when you implement this, you don't get some errors. Note that last week we were expecting to receive NumPy arrays on this function, for example, and we converted it into a constant, into a TensorFlow constant to get the corresponding tensor before doing these multiplications. Now we are doing everything in tensors here, and we first convert to tensors with the correct type, float32, so that this is the same type as the variables that we have. I forgot to put there the type. But we convert everything to TensorFlow, to tensors, before sending to the graph function there and to the gradients and so on. The reason for this is that these functions that you create with the function decorator can automatically convert NumPy arrays into tensors, and will create different graphs depending on the dimensions of the tensors and so on. But when it's done automatically, sometimes you get strange errors that you don't know how to diagnose. So one of the tricks here is to do everything ourselves, convert everything to tensors, and then send exactly those tensors to this autograph part before creating the graph. And this part, we are only going to use it to see the graph visually, but this is very useful to improve performance, because if you give TensorFlow the complete compiled graph to execute, then TensorFlow can decide which parts to send to the GPU, to the CPU, and how to manage everything much better than when it's running one line at a time and doing all the computations one at a time, because you cannot see the whole picture to optimize the distribution. So if you need to have a better performance, then you can use autograph and run. We're not going to do that because there are lots of tricky details that you need to take care for doing that. And since we're going to use Keras for more complex networks, then we don't need to worry about things at this level, because Keras takes care of all of these messy details automatically. But for now, what we're going to do is to take a look at the logs we created. So if we run this, we have a log. It's still not training, so it only has the graph with the computations. But we can now run Tensorboard in the same folder. So we have a root log folder called logs. This is a folder that is a subfolder of where we are running the code. And inside that folder, we have one for each time we run the code. So now, in that folder, in the main folder where we have the code, we can call Tensorboard and give this argument, logdir, the main logs folder. So this would be the logs, the logs folder that we created. Now, if you're using Windows, if you use the Windows command prompt, probably you'll have an error here on the Tensorboard, because Windows does not know what Tensorboard is. You need to use the Anaconda command prompt for this, because you have everything installed in Anaconda. If you have Linux, probably you have something a bit better configured, but Windows is a bit messy in these things, because Windows does not expect users to use the command prompt, so it's always difficult to do this kind of thing. But if you use the Anaconda shell prompt, this should work. Now what this does is it runs Tensorboard, and Tensorboard is a server where you can connect with the browser. So open your browser, point it to this address here. So 127.0.0.1 is just a loopback address. It's the address of your own computer, whatever the computer you're using. And this is the port where Tensorboard is running. So 6006 looks like Goog. That's why it was chosen. Okay. So now you can see in your browser the interface with Tensorboard, and you can see the run that you did. And if you show the graph, this would be the computation graph that we have. So we have here, you can see more details, but you should have the multiplication of your weights by the input, add the bias to get the net here. Then you have the logistic loss function, and you have all the gradients necessary to compute to do the backpropagation and adjust the model. So everything here built by your own computations and by the gradient tape, because remember that we are creating the graph inside the gradient tape here. So the context of the gradient tape. So gradient tape will also add to the computational graph everything it needs to compute all those derivatives with respect to the variables that we want. So everything will be here, and this will be a fairly complicated graph because we need everything, both what we're computing and all the gradients. And now we can also add values to Tensorboard as we run. So for each epoch, we are going to create here the batches of the features and the target labels. Note the difference here from last week. Last week we were using NumPy arrays here, But now we have everything set up to use tensors, so we create the tensors from the slices we are taking from our data. And now we send those tensors there, we apply the gradients, and for each epoch we compute the logistic loss, and we write into the log for the epoch we are in the loss with this label, train loss. So if you just want to write a value, a scalar value to do a plot, you use this scalar method here on TF summary. Note that we are using our writer as the default writer, so it's going to write into our particular log. And we can put the label, the value, and the x coordinate, which is the step we are on. So typically the steps will be the epochs, so that we can then trace the loss function over the epochs. If you do this, you can now go to Tensorboard, and even as you are running the training the network, you can see the plot appearing there, and you'll see this strange result here. So this lighter line is the actual values, a line through the values. This is a smoothed line, which you can adjust the smoothing on Tensorboard if you want. But then we're going to see some interruptions there, these points here, which occur because some of the values are not a number. There is a problem here during training. So if you see the printout during training, you can see this. This happens when you have some overflow problem and you start to have numbers that you cannot represent. For example, in this case, in 32 bits floating point representation. And the reason for this is this logistic loss function. We are computing here the logarithm of the predicted probability of belonging to the class. The predicted probability is the sigmoid activation function, which varies from 0 to 1, but it's never actually 0. It goes closer and closer to 0. However, the logarithm of that going closer and closer to 0 will be increasingly negative here. And if we were to plot this as a function of x, since this one is going closer to 0 but never 0, this one is always going down, and it's the logarithm of the sigmoid will be a straight line on this part here. But since we are doing this with a finite representation, any rounding error, for example on the sigmoid, will now give us a logarithm of 0, and then things break down. So this is a very unstable computation to do on the computer, because the logarithm of something that approaches to 0 will approach minus infinity, and the sigmoid is approaching 0. So any small deviation there, and we have not a number, we have an overflow problem. So solutions for this are basically to create an expression that does both things, the sigmoid and the logarithm, in a way that is computationally safe. For example, this is one solution, which is when the input to the sigmoid is below minus 33, so we are very far away here, we take just the same value. So it's this straight line on this part. And then in other intervals we take these different expressions. Tensorflow uses this expression here, but basically what we need to do is not to step first into the sigmoid and then the logarithm, because that combination is potentially explosive. What we need to do is to short circuit everything and compute this function here, the red one, which is the logarithm of the sigmoid, in one go without having that danger. So in TensorFlow you have this sigmoid cross entropy with logits. You see the cross entropy appearing all the time, but it's the logistic loss with logits. The logit is the value that is the input to the sigmoid function. So the idea is that this function computes this plus the sigmoid there, all in one go, using a safer expression that will not give the overflow. So what this also means is that you need to give this function not the output of the sigmoid, but the input to the sigmoid, which is the logits, the linear part of the neuron. So we're going to split our computation into two different regimes, two different applications. One is when we are predicting the probability of X belonging to a class. In that case, we do the multiplication with the weights, we add the bias, and then we apply the sigmoid activation so that we have the probability of belonging to the class. But when we are training the network, we don't want that, because if we apply the sigmoid and then the logarithm, we run into problems. So when we are computing the logistic loss, what we do is we use this logits function that is similar to the prediction, but does not apply the sigmoid. It just computes the linear part of the neuron and returns that linear part. And now when we are computing the loss function, we take the logits, we reshape that for a single dimension. We do the same for the label so that we have two vectors with one dimension. And now we compute the mean of the sigmoid cross entropy with logits between these two. So this one is going to do the equivalent of using the sigmoid and then the logarithm without blowing up the numerical representation. Okay? So the reason why we need these two branches is because when we are using the network for prediction, we want the output of the sigmoid activation because we want the probability. But when we are computing the loss function for training, we want to go around the sigmoid and put everything together so that we don't have these numerical problems. Okay, so now if we do this, we can train. Remember that now for the loss function that we're going to put in our log, we also need to use the new function, the logistic loss here, because otherwise we could get, again, not a number in some cases there. And now you can see that it works, we don't have that problem anymore. So you can use these loss functions in TensorFlow. The mean squared error is not really important because it doesn't have this problem of the logarithm and the sigmoid and so on. It's just the square of the difference, so that's stable. Whether you implement it or use the one from TensorFlow, it's not a problem. But these sigmoid cross entropy and softmax cross entropy, they expect to receive the logits or that linear part that goes into the sigmoid, so that they can compute things safely, the combination of the logarithms with the sigmoid. So let's see an example here, a regression with the multi-layer perceptron. We're going to use this auto mouse per gallon dataset, which is a dataset that has features of cars, like the power, the year it was built, and so on. And we're going to try to predict how many miles per gallon the car can do. So basically the consumption of the car. To do this, this is derived from this data set that you can find at the UCI repository. I took out the categorical features and cleaned up the data a bit. But the idea is that you're going to shuffle the data before splitting into training and validation. The target value is the first column, which is the number of miles per gallon the car can do. Standardize the features and the target. So standardizing the features, we saw it's important to give the same scale in all dimensions on the input to the network. Standardizing the target on a regression problem is useful because it allows you to use the same range of learning rates, for example, have the same idea of what a reasonable error should be. Because if you have a mean squared error of 0.7, this is very different if you are in a range around 0 and 1 or something like that, or if you are in the range of thousands or millions. And so one useful thing about standardizing the output is that you always have the same scale on the values that you have there, and this may be useful for your experience of whether things are going right or wrong. Another thing is that if you have an output value that is higher, And if you're doing the squared error function, you can have a loss function that is really very high, because if you're missing, say, by 10 units, then the quadratic error will be 100. And that will also influence the size of the gradients, and in turn you may have to compensate that with the learning step. So if you use different scales for different problems, you have to keep adjusting the learning set, the learning rate to different scales, and this may be a bit of a bother. If you standardize it, then your experience will always be with the same range of values. So this is my recommendation: standardize when doing a regression, standardize both the features and the target value. Of course, when you're doing classification, don't standardize the target, because in that case it would not make sense. Use a linear output for the last neuron. You only have one neuron on the output because you are trying to predict the miles per gallon value. It's only one value. Use a linear output because you are not putting any constraints on that value. The mean squared error loss function is the one that corresponds to minimizing the likelihood, to maximizing the likelihood, when we assume that there is a normally distributed error on the prediction value. And you can now try different activations and learning parameters on the hidden layers. Remember that the output layer should be linear, but the other layers can be as you want. So basically, load the data, standardize everything, retain the scaling values that you used for standardizing, not only so that you can apply the same thing to new examples if you want to predict them with your model, but also so that you can then convert the output of the model into the correct units of miles per gallon. Because remember that once you standardize, you have some arbitrary units in your model so that they range around 0 with a standard deviation of 1, but then you have to put it back on the physical, the meaningful units that you use. To create the model, we can make the code a bit better than what we had before, which was just doing all of those multiplications and so on. We can create a function that builds a layer of our multi-layer perceptor. So what this function needs is to have the matrix of the inputs so that it knows how many columns the inputs have. Because the number of columns in the inputs to the layer is the number of features, and this corresponds to the number of weights each neuron must have. So the rows on the weights variable will be the same as the columns on the input. And the columns on the weights variable will be the number of neurons. So we can say that we want, for example, 5 neurons, we give the inputs and it can do this. And then we create a variable here also for the bias, but with as many values as the number of neurons that we have. There is this layer name here that I can show in the future, but I forgot to delete there, so ignore that for now. We also now create a function to stack a sequence of layers and create the whole method. So basically what we need is a list with the number of neurons for each layer that describes the set of layers. And now we start from the input matrix, which is this X, and now we go through all the layers and create a new layer that takes what came out of the previous layer and puts it into this number of neurons. So we can use this name variable here, but this is a simplified version there, but you can actually give names to these variables, create a scope and so on. I'm going to show an example later. So currently with this version we are not actually using that name, but you can name each layer in the computation. And now what we're going to do is to make it easy to compute the activations of the network, we're going to consider each layer to be a pair of a weight matrix and a bias vector. This is what we've been using before. We multiply by the weights, we add the bias. So this is what we're going to create here on the network, all of these tuples, weight and bias, weight and bias. This makes it easy to compute then the activations. But for the gradient tape object and for applying the gradients, we need a list with all the variables, and it cannot have these tuples. It cannot have this structure. It must be a flat list. So this is why we create two things here. The network is a list of tuples with all of these tensors, and the variables is a list with all the tensors flattened out in one go. So basically, we use append here and expand here so that we create a flat list on this case. Now, this is important because the dimensions of the input to the second layer will be given by the matrix of weights of the first layer, because this tells us how many neurons we have on the first layer. So we keep moving forwards on the network and using each layer as the input to the next one. Okay, so with this we can now create a network. We need a function for prediction, so we can do this when we receive the tensor x for the prediction. We can loop through all the pairs of weight bias in our network and do the multiplication and apply a leaky ReLU. We do this for all except the last one. So all the hidden layers of the network are leaky rectified linear units. The last layer of the network, we just multiply the weights by whatever came out of the previous layers, and then add the bias and return the value. So the last layer is a linear neuron there. We are not applying any activation function. If we want to create the graph, we can use the same thing as before. So in this case, I'm only showing the graph for the prediction here, and I can write it to the log. So this would be how it looks like. So this is an example with this number of layers, 3 layers. So we have this output neuron here. This is one hidden layer. This is the other hidden layer. We can simplify this graph by adding names to these operations. So instead of just doing this multiplication and adding the bias, we can create a scope here, a name scope, with some string. Note that these names should be the kind of names that could also be valid variable names. So don't put strange characters or spaces or things like that. But in this case, this will be the number of the layer. So layer underscore the number of the layer. Layer starts at 1 and it keeps increasing during the loop. And now inside this name scope, I put all these operations, the multiplication and the activation. What this does for the computation, it's indifferent, it doesn't change any computation. But on the autograph, it creates this representation. So this is layer 1 that you can then expand if you want, and you see the actual operations inside there. But when you give a name scope, it creates just a box with all of those operations there. And this gives you a better representation of the network, where each hidden layer has layer and a number, and then the output is called output. So you can see this network with 3 layers, where the last one is the output. Now, I suggest that you use a small learning rate, otherwise you're going to have numerical problems here. Remember that you need to add the mean squared error loss function. I didn't show that here, and all the training and so on. You may have problems again with not a number. So the problem this time, if you use a large network, maybe that the initialization weights of the network are too high, and when you have many neurons adding their activations together and several layers, you start getting values that are too high and things explode again. So one adjustment that you can do is, instead of beginning your layers with a random normal distribution with a standard deviation of 1, you can do it with a standard deviation that is 1 over the number of neurons in the layer. So the more neurons you have in the layer, the smaller the weights will be initialized, so that you avoid this problem. There are more sophisticated initialization methods. We're going to talk about them in another lecture, but you can experiment with this one for now. And then, at the end, you can write the training and validation error by converting your loss function into the miles per gallon units. Note that we standardized everything, so we have some arbitrary units that are around -1 to 1, so around 0 with a standard deviation of 1. But now we want to present our error in miles per gallon. So this is the loss function, is the mean quadratic error. We take the square root of that and we take the square root of the mean of the square. So this is the root mean square deviation, the RMSD, which is in the same units. And now we multiply by the standard deviation that we used to divide in the beginning. So now we convert things back into miles per gallon, and now you can plot the error. But note that this way, this different scale of miles per gallon is not affecting the gradients or the step, the learning rate or something like that. You're only doing this after everything is computed for plotting the data. Another exercise that you're going to do is to use Softmax for multiclass classification. We're going to use the MNIST dataset. So this is a dataset of images of handwritten digits. And each image is 28 by 28 pixels, and they have classes for 0, 1, and so on. You're going to create a multi-layer perceptron for trying to classify this data, but first you need to obtain the data. You can do that by importing this data set here from the carriage data set. So basically you have this load data function that will load all the images that you need. If you don't have them in your in cache, in your installation of carriage, it will download from the internet on the first time you use, but after that it will just use the cached version, so you only need to download it once. You need to reshape this to 784 features because these are a set of images. They came in 2 dimensions, but we're going to use a multi-layer perceptron. So each example will be a vector of 784, which is the number of pixels each image has. So we're going to use each image as a vector of the pixel values. The pixel values are the intensities of the brightness depth. Use 50,000 for training and 10,000 for validation, and you can leave the test set. So basically the training set here is 60,000 images. We can use 50 for training, 10 for validation, and then you can test at the end if you want in the test images. Remember to use the Softmax cross entropy for the loss function because you're going to use the Softmax output, and remember to give it the log x, otherwise you'll have problems with the numerical stability. But then use Softmax for the actual prediction. So this is the same trick as we saw before. We have one set of computations for the prediction that apply the Softmax activation, and the other one short circuits that activation and puts everything in that loss function. We also need to use one-hot encoding for the labels. These train images and train labels, the train labels is a vector of 0, 1, 2, 3, 4, and so on, which are the digits that you have here. So each image is associated to a label between 0 and 9, an integer. But the output of our network is a set of 10 values that we apply Softmax to, so that we have the probabilities of the 10 classes. In order to train that, we must compare it to a vector that describes the class our digits are in the same format. And this is called the one-hot encoding. So if you have something that is in this class, you create a vector that says it's 0 on everything except this class. This would be the target probability distribution for this example. 1%, 1 probability of being in the right class, 0 probability of being in the wrong classes. Okay? So we have to convert all the integer labels into these vectors. But this is easy to do because we have a function that does this, two categorical, in the carriage utilities. So it basically takes the labels that are integers and converts them into those one multi-coded vectors. If you want to measure accuracy, or if you want to convert the output of your network, which will be something similar to this, into a single integer telling you which is the class with the highest probability, you can use the argmax from NumPy and determine which, for each vector, which is the class your network is predicting. Okay, so this is what you're going to do. Create your network, try different activation functions. Okay, if you have a deeper network, sigmoid will not work very well. Try different rectified linear units. Try different networks, dimensions, number of neurons, and check the validation data for overfitting. Check the training loss to see if things oscillate too much, because if they do, you probably have a learning rate that is too high, and then try to optimize this as best as possible. So basically what we saw here was just a quick pass through the graph mode. This is useful for optimizing performance and also to visualize the graph in Tensorboard, but mostly for optimizing performance. We are not going to return to that. This is just so you know you can use that. Tensorboard will be an optional thing that you can use to follow training if you want. It's easy to use and allows you to plot the loss values and so forth. But then the important part here is to remember why we need to sometimes use the logits into the loss function and use those specific loss functions from Tensorflow to avoid numerical stability. Also, problems, numerical stability can occur if you have a learning rate that is too high, if your weights are initialized to values that are too high, and so on. And basically for the exercises, you're going to do this plus a binary classification with the banknotes data set also. So we cover binary classification, regression, and multiclass classification so that you use the different activation functions and loss